Hello everyone, welcome back to my channel. In this video, I will explain the step-by-step procedure for finding the solution to a linear programming problem by using graphical method. But before getting into the topic, I kindly ask you to subscribe to my channel. Now let's get started and discuss the topic in detail. Now let us see the step-by-step procedure. So first, develop the LP model. That is, state the given problem in mathematical form, as we have discussed in the previous video. See in my channel how to convert the data into mathematical LP model. Next, step 2. Plot the constraints on a graph paper and decide the feasible region. That is, replace the inequality signs, that is greater than or less than. So replace them with equality sign and find the coordinates for each constraint and draw these points as a straight lines on the graph paper and decide each time the area of feasible solution according to the inequality sign of the constraint as shown in the figure. So once after converting the inequality to equality, then we'll find the coordinates and plot them as a straight line. Here are the three equations and we have plotted the straight lines. And next, the final shaded area is called feasible region of the given LP problem. At any point inside this region is called feasible solution. And this provides the value of x1 and x2 that satisfies all the constraints. Next, step 3. Now, examine the extreme points of the feasible solution space to find the optimal solution. The first step is determine the coordinates of each extreme point of the feasible solution space. As now here A is one of the extreme point and B is one of the extreme point, C is one of the extreme point and D is the one of the extreme point and 0 is the extreme point. And the area which is lying in between these coordinates is called as feasible region. And here x1, x2 will be satisfied. Now compute and compare the value of objective function at each extreme point. Say for example, here if we take a point that is 0, 40. Now substitute this coordinate in the given objective function that is z function and compute the value and compare all other coordinates. Now let us find the solution with an example. Use the graphical method to solve the following LPP. Maximize z equals to 15x1 plus 10x2 subjected to constraints 4x1 plus 6x2 less than or equals to 360, 3x1 less than or equals to 180, 5x2 less than or equals to 200 and x1, x2 greater than or equals to 0. Here are the three constraints and one non-negative constraint. Now let us find the solution. So first step is convert the data into LP model. So here the given LPP is already in mathematical form. So treat x1 as the horizontal axis and x2 as the vertical axis. x1, x2. Plot each constraint on the graph by treating it as a linear equation and then the appropriate inequality conditions will be used to mark the area of feasible solutions. Now let us see the in detail. That is, consider the first equation 4x1 plus 6x2 less than or equals to 360. Now treat this equation as 4x1 plus 6x2 equals to 360. For this, find any 2 points that satisfies the equation and then draw a straight line through them. The 2 points are generally the points at which line intersects the x1 and x2 axis. So for example, x1 equals to 0, x2 equals to 60. Similarly, x2 equals to 0, x1 equals to 90. Then these 2 points are then connected by a straight line. Let us see how they will be connected. So first assume x1 equals to 0, then we'll find the x2 value, as we'll get the coordinates as 0 comma 60. Similarly, now we'll assume x2 as 0 and we'll find the another coordinate. So that is 90 comma 0. So here we got the two coordinates. Now plot them on the graph and connect them with a straight line. But here there is a question where these points satisfies, that is inequality sign or inequality condition. At any point above the constraint line violates the inequality condition, but below the line does not violate the constraints. So the inequality and non-negative conditions can be satisfied by the shaded area, which is called as feasible region, as shown in the figure. Similarly, the constraints 3x1 less than or equals to 180 and 5x1 less than or equals to 200 are also plotted on the graph. Let us find the coordinates. So that is x1, x2 is already 0. So x2 equals to 0. Now 0 comma 0, x1 equals to 0. So x1 is 60. The two coordinates are 0 comma 0 and 60 comma 0. And similarly for the 5x2 less than or equals to 0, we'll get the two coordinates, that is 0 comma 0 and 0 comma 40. So totally we got 6 coordinates. So 6 coordinates can be converted into 3 lines. Now let us plot all these coordinates in the graph. Take a graph and draw x1 and x2, as x1 is horizontal and x2 is vertical axis. Now select the suitable scale as per our convenience and plot the coordinates. First, let us take the first equation, that is 4x1 plus 6x2 equals to 360, and the coordinates are 0 comma 60 and plot in on the graph here. So 0 comma 60, and next 90 comma 0, plot on the as x1 equals to 90 and x2 is 0. Here we'll plot the point. Now connect these two points. So those blinking points are connected with a straight line, and name the straight line with the given equation only. Now take the second equation, that is 3x1 equals to 180. So 0 comma 0 and 60 comma 0. So as first point is 0 0, so we'll plot the second coordinate only. Point the 60 comma 0, that is x1 equals to 60, x2 equals to 0. First coordinate is 0 comma 0 and second coordinate is 60 comma 0. So here the blinking point is the 60 comma 0. From here draw a line which is parallel to x2, as the first coordinate is 0 comma 0, and mark it as second equation. Similarly for 5x2 equals to 200, 0 comma 0 and 0 comma 40. Here x1 is 0 and x2 is 40. So here from the blinking point draw an horizontal line which is parallel to x1. So now we have plotted all the given points. Since all constraints have been graphed, the area which is bounded by all the constraint lines including all the boundary points is called feasible region or solution space. So here the feasible region is shown in the figure by the blinking points, that is O, A, B, C, D. Since the optimal value of the objective function occurs at one of the extreme points, that is here blinking points of the feasible region, it is necessary to determine their coordinates. The coordinates of extreme points of the feasible region are 0, 0 and 0, 40, 30, 40, 60, 20 and 0, 60. So these are the extreme points. Now evaluate objective function value at each extreme point of the feasible region. Now evaluate the objective function value at each extreme point of the feasible region. So first draw a table. First point is extreme point and take the extreme coordinates and objective function and calculate the objective function. As we got the extreme coordinates O, A, B, C, D, we'll substitute each value of the coordinate and find the maximum value. So next at point A 0, 40. So that is 15 into x1 is 0, x2 is 40. 15 into 0 plus 10 into 40. So the value is 400. Similarly, at B 30, 40. So substitute this value in the objective function. 15 into 30 plus 10 into 40. So 850. Next, substitute the value of C 60, 20 and compute in the objective function, that is 1100. Similarly for D 60, 0 and the objective value, that is Z value is 900. Since objective function Z is to be maximized, from the table we conclude that maximum value of Z is 1100 is achieved at the point extreme B 60, 0. Hence the optimal solution to the given problem is x1 equals to 60 and x2 equals to 20. So Z equals to 1100. Let us see the minimization problem. Use graphical method to solve the following LP problem. Minimize Z equals to 4x1 plus 3x2 subjected to constraints 200x1 plus 100x2 greater than or equals to 4000, x1 plus 2x2 greater than or equals to 50, 40x1 plus 40x2 greater than or equals to 1400 and x1 x2 greater than or equals to 0. So here the objective function is minimization and the constraints are 3 constraints and 1 non-negative constraint. As we discussed earlier, the inequality sign should be replaced with equal and find the coordinates and plot them on the graph. Now let us find the coordinates by using each constraint. So here first constraint is 200x1 plus 100x2 greater than or equals to 400. So here to simplify the equation, divide the equation with 100 on both sides, which can be written as 2x1 plus x2 greater than or equals to 40. As we discussed earlier, the step 1 is replace the inequality sign with equal sign. So which can be written as 2x1 plus x2 equals to 40. So now to find the coordinates, first let us assume that x1 equals to 0. So if you substitute x1 equals to 0, then you'll get x2 equals to 40. Similarly, now assume x2 equals to 0, then x1 equals to 20. So the first coordinate is 0, 40 and the second coordinate is 20, 0. Similarly, for the second equation. So x1 plus 2x2 greater than or equals to 50. So now replace the inequality sign with equality, that is x1 plus 2x2 equals to 50. Next, similarly, take x1 equals to 0. So if x1 equals to 0, x2 equals to 25. So next, x2 equals to 0. Then x1 equals to 50. So the coordinates are 0, 25 and 50, 0. Third constraint, 40x1 plus 40x2 greater than or equals to 1400. So here we can simplify this equation by dividing 40 on both sides. So which can be written as x1 plus x2 greater than or equals to 35. So similarly find the coordinates for this constraint also. That is, if I assume that x1 equals to 0, then x2 equals to 35. If x2 equals to 0, x1 equals to 35. So the first coordinate is 0, 35 and the second coordinate is 35, 0. Now let us plot all the coordinates in the graph. So the first equation is 2x1 plus x2 greater than or equals to 40 and the coordinates are 0, 40 and 20, 0. And the second equation is x1 plus 2x2 greater than or equals to 50. And here the coordinates are 0, 25 and 50, 0. And the third constraint is x1 plus x2 greater than or equals to 35. And the coordinates are 35, 0, 0, 35. Now plot all these coordinates on the graph. So take an graph paper and draw the x1, x2 as x-axis and y-axis respectively, and plot the coordinates as per suitable scale and plot all the coordinates. So the first coordinate is 0, 40. So here is the 0, 40. And next is 20, 0. So connect these 2 points with a straight line. So mark it as 1. Next, similarly, x1 plus x2, 0, 25 and 50, 0. So 0, 25 and 50, 0. Connect these 2 points with a straight line. Next, third one. First coordinate is 0, 35 and second coordinate is 35, 0. Connect with a straight line and mark the lines with the respective equations. Now identify the common, that is feasible region. After plotting each constraint and treating it as a linear equation, then use inequality sign of each constraint to mark the feasible region by shaded area as shown. This is the feasible region. Now the coordinates of the extreme points of the feasible solution are, the first one is 0, 40, assume it as A, and B is here, it is the point B. B is 5, 30, and next third point 20, 15, take it as C, and D is 50, 0. So here the feasible region is away from 0, 0 because as constraints are greater than or equals to. So the feasible region will lie above the lines only. Now Let us find the Z value. So here the first column is extreme points, and take the coordinates, that is extreme coordinates, substitute the values of extreme points and compute them and compare for the minimization value. So first A is 0 comma 40. So when I substitute in the Z function, I'll get 120. Similarly B 110, C 125, D is 200. So here the minimization value will occur at B. So x1 equals to 5 and x2 equals to 30. So objective function z equals to 4x1 plus 3x2. We will get, when we substitute x1 and x2 as 4 into 5 plus 3 into 30 as 110. So z value equals to 110. In conclusion, the graphical method is a powerful tool for solving LPP. If you found this video helpful, please like, share, comment and subscribe for more videos. If you have any questions regarding mechanical engineering, please email us at drawingforengineers@gmail.com. We'll respond with a video explanation. Thank you for watching and see you in the next video.